Hi, hello everyone. Last time we left off, well, basically with this spinning quad, if you want. But the point was we did all this kind of transformation matrices, right? We did translation, scaling, and rotation. And this time we're actually going to deal with projection. And we're going to cover easy of the two matrices for projection, the most common used ones. And that's an orthographic projection. So you can see this type of projections, and the orthographic one is one that actually doesn't have like this depth, so it's not real 3D, but it's quite useful for rendering sprites. And maybe in some cases, if you want to do this isometric kind of game, cabinet oblique, not even sure, never used that. But the point is, it doesn't have like perspective here. It doesn't have this depth information, right? It just kind of drops parallel to a plane, and that's it. But the use of it is like I mentioned for sprite rendering, because in WebGPU, right, and in most common rendering APIs, the device coordinates, right, normalized device coordinates go from -1 to 1, -1 to 1, and z, that kind of depends, right, on the API. In WebGL, I think it's -1 to 1, but in WebGPU, it's kind of 0 to 1. So what does that all mean? So it means that let's just get rid of this. It means that the device coordinates go from here to here, and I think here it's -1 and here it's 1. And what we want to do with the graphic projection, we can do like this kind of stuff. So we can forget this and say let's go from from 0 to 800, and that's one way to think about it as well. So it's kind of like mapping from one space to another space. So I also like to think of photographic projection like that, just mapping from 0 to 1. Sorry, this is 800 space to, let's say, -1 to 1. So first things first, we actually need to somehow paste that matrix into our shader as well. So let's start with that. And for that, we can just go to our shader that we had last time. So how are we going to do it? So we had this group 0, which is going to remain same as it is, but we're going to change these groups to 2. So these groups where we had our text sheets now 2, and this diffuse color group is now group 3, and here we're going to have group 1 and then binding 0. So why group 1 instead of group 0? Well, because this is kind of like data per material, and this will be the camera property. So we just need to paste it once and then forget about it. But this we actually need to paste more times. So they're kind of unrelated data. So that's probably why. So we can just call it view projection if it's of type matrix 4x4, similar to our transform. And then we can just paste it here and multiply it. Okay, good. So next step is we just need to fix our shader and maybe create a camera class. So let's first deal with our buffer. And for camera, let me see how I'm going to do it. I have some tips. Okay, so it's just going to be export class camera. Then we're going to need our buffer as usually. So we created this uniform buffer wrapper around GPU buffer, right? If you remember. And we're going to have private projection view, and it's of type matrix. We can just set it to matrix 4x4 identity. So it's going to be identity matrix by default. We're going to have set. So whenever we set projection view, we're also going to update buffer as well. And then we just need to have constructor. As usual, we need device, GPU device. And then we can create a buffer. So let's see, these are good suggestions. So usually we use device, then our camera, and then we can just call this camera buffer. All right, that's it for the camera. And then in our unlit render pipeline, here it's always a bit more involved. Okay, let's see, how am I going to do this? So we're probably going to need another bind group. So we had vertex bind group, this is texture. I can just call this projection view bind group. Okay, here we don't have to do anything, and as a dependency we're just going to paste camera here. So we're going to inject it, and it's not going to be uniform buffer. We can actually paste our object. It's a bit easier to work with that way. So let's see, what did I have here? We had buffer layouts, that's not of our concern. Okay, we can create that bind group. So this, sorry, we need bind group layout first. So projection view, layout, binding 0 on vertex stage, and the buffer, right? So that's the projection view group for camera. Projection view group layout, so we need to paste it in somewhere over here if I remember correctly. Just so that in our groups. Sorry, let's see. Aha, here. My bad. So it's going to be here. It's going to be group 1, but as I mentioned, we're going to move this to group 2 and group 3. So we have our projection view bind group, and we're going just to need layout. We paste in layout, and then we need to create bind group, and they were here. So right after vertex bind group, we can create this projection view bind group, create bind group. So layout, projection view, layout, and then here it goes 0 because it's binding 0, and then we, for the buffer, right, resource buffer, we use camera buffer, right? So this is our GPU buffer. Finally, and then one final step, we just need to paste it in. So we moved these groups a bit down, right? And then set bind group 1. And finally, final step is just to create that camera. Let's see, we can just do it somewhere over here. We need device, and then we need to paste it to our pipeline. And now it might work. Oh, well, it does. Okay, perfect. So if you got stuck or mistyped something and it doesn't work, please just look at the GitHub code, which is linked in the description of the video. No need like to get lost in some, because this is a bit messy, this sunlight render pipeline. I admit it's a bit messy, but the WebGPU is very descriptive, so it is what it is. So next step, we can just start in our matrix class. And I was a bit annoyed, sorry, by this name, create translation matrix, so I'm just going to rename that to translation scale. I think it's a bit easier, and then rotation Z, because it's around Z axis, and then we're going to have public static orthographic projection. So I'm going to explain these parameters, but you can type them for now. So we're going to have left, right, bottom, top, near, and far. That's quite all right. And then we can just create our matrix. So here it's already setting something, so let's just ignore that and say by default it's going to be identity matrix. And then we're going to discuss what we need to do to actually create this orthographic projection. So okay, so let's start with this. So let's imagine that we want to move our space so that here it's -5 and here it's 5, right, in x direction. So how can we do that? Well, we can use that orthographic projection, sorry, but what I'm going to do is just describe this a bit. So actually, let's see what we're trying to do. So if we have our coordinate space, let's just, I'm just going to draw this, maybe it can be a bit bigger. Anyway, so, and let's say that our space is somewhere over here, and we have -1 to 1. And what we want to do is create, let's say, here somewhere 5, and then have -5 as our coordinates. So let's say that we want to have our object somewhere here or somewhere here, doesn't matter. But if you do that, right, if you just go something over 1, it's going to get bigger, and then it's going to be clipped out of space. You're not going to see it anyway in your device. And what we want to do is, so this is just an x-axis, right? The same applies for y, and z is a bit different because z coordinates go from 0 to 1, right? And here it's -1 to 1. But anyway, so what we wanted to do is, let's say that we want to have somewhere over here like 3x. So how can we achieve that? So if we know that our space here, let's call this right, and let's call this left, and we have this kind of size of the space. So what's the size of our space? Well, it's right minus left, and what would that be? So we have 5 minus, and here it's -5, so that becomes a +5. So we know that our space is 10 units. So we can just divide our x, right? We can use our x and divide it by this size. So we can divide it with right minus left. But notice here that our original space is 2 units. So we can just say, sorry, it's probably better like this, 2x, right minus left. So what are we going to have? So if we have, for example, here 3, it's going to be 6 units over, right? We already determined that this is 10, 6 over 10, so that's kind of like, what's that actually? So we can just, it's like 3 over 5, right? It's 3 over 5, it doesn't matter, but it's going to be somewhere over here, right? If you agree with me. So somewhere over here, it's actually going to be mapped to this space. So let's see how it works. You're going to get it now. So let's just try to do this. So what did I mention, right? I mentioned that we have this space, and let's try to do that. So let's say that we have here, and I'm going to also explain why it is here in this part right after we code it. So we're going to have something called R0 C0, and that's just a placeholder for row 0 column 0, so you don't have to think about it. So what did we have? We had 2 over right minus left, right? And then we can do the same for y, and here it's going to be row 1 column 1. And for z is a bit different, right? Because I mentioned that z space goes from 0 to 1. So to get it, you just need size of z space divided by 1. So it's going to be 1 over, let's say, far minus near space. All right, let's try to actually do that. So we're going to have R2, C2 is, it's actually 1 over far minus near, and we can actually place them here. Okay, we're not using it yet, so let's go to our main, and I'm just going to fix this texture tile because it's annoying like this. But let's say for our camera, so you can already see we're still in original space, but let's say our projection view is going to be orthographic, and I'm not going to use these coordinates. I'm going to use -5, 5, -5, 5, and here we can just leave it 0, 1, right? You can already see that it works. So and let me just get rid of this rotation as well, because it's a bit annoying. So yeah, here it's going to be actually translation, and let's say -4.50, right? So as you can see, what I did here is we changed our space, right? Our original space was going from -1 to 1, like I mentioned, but now it's at coordinates minus, why is it not typing? A bit weird. Okay, my usual software doesn't work for drawing. Okay, I had to manipulate it for some reason, but we had -1 to 1, and now it's actually -5 to 5, right? And as you know, the origin of our sprite is in the center, and I just moved it to -4.5, right? And so therefore the position is here. If it was at -5 exactly, then you would only see half of it, and we can confirm that. So let me just do this. Bit annoying. I'm not a fan of Mac windowing, I have to say. It's a bit annoying. There is probably some shortcut there. But anyway, so if I was just to move it to -5, you would see probably half of it, right? And then if I was to move to -3 and let's say -5, it should be somewhere at the bottom, and it is, and that's how it works. So let's just go with 0, 0. So now we know that. And what was I trying to explain? Why are these values in our matrix here? Well, it's actually really simple, right? Why are they here? Because if you consider our original vector, it's x, y, z, and then we had this, but this is not important right now, right? We can just imagine this as 3 by 3 matrix. So right, we had this equation that I mentioned, 2x, and then we had right minus left, right? And it goes over here, right? This belongs to here. So what does this do? Well, because x is multiplied by this, so x is actually not here. It's just 2 over right minus left. And when you multiply this x, you actually get x here, right? And then this is 0, this is 0, this is 0. Therefore, you can ignore all these values. They're not important. And the same is true for y. Y gets multiplied by the value here. Z gets multiplied by the value here. Here it's 0. Here it's 0, 0, 0, 0, 0. Anyway, it's called the scaling part of the orthographic projection because it scales this space, right? So that's kind of how it works. Hopefully the explanation is not too complicated, but you just, if you do the math, it's going to be easy. And now the second part that we want to do with our matrix, since we have this, is actually translation part, right? If you remember, we had this scale matrix, and this is exactly as a scale matrix. So we just scale our coordinates to fit into this -1 to 1 space. And here we're going to do now translation part here. So let's call this const, and we're going to actually solve for this equation here. Let's try to do that actually. So okay, let's see what we're trying to do. Let's say that we want to have our left space, and then we have our x, and it needs to be in this space. So what do we want to do? Well, our x, we know that it needs to be -1 space to 1 space, right? And if you followed my metal video, it's kind of similar to, it's exactly similar to that. So we just need to solve this equation. So what can we do? So we need to have here -1 and here 1. So first we can get rid of L. So we can just say everything minus L. Right, so we have 0 here, we have x minus left, and then we have right minus left. So here we can also get rid of this part, and we can just say, okay, it's going to be 1, right? We want to have 1 here, so we can just do this. We can divide everything by this side, and 0 divided by this is still 0. So we have 0. X minus L, right, minus L. I'm not sure why I'm typing this second time, but here it's just 1 now, right? So we can now move it to, we can just do ×2 so that we can solve this bit further. So 0 times 2 is still 0, so we have 2x minus left side, right, minus left side, and then we have 2 here. We just multiply each side by 2. So here we can just now it's easy to move it to -1 to 1 space, right? You just subtract everything by -1, -1, -1. So let's just do that. 0 minus 1 is minus 1. So we have 2x minus left side, right minus left side. And this 2 is actually before equation. It's just my poor typing. And here it's now 1. And I forgot minus 1 here. So we can rewrite this 1 as right minus left side over right minus left side. So we have this 2x minus left, right minus left, and we can rewrite this right minus left. And now we can easily solve for x, so we need to have an x here. So let's see how it's going to look like. So we have this, we have 2x minus 2l, and everything right minus left, and then we have plus right or minus right, since this is changing, so it should plus left side. Okay, let's see. Let's see, we have minus 2l, and so we're just left with minus l, right? So let's rewrite this here. And this can change because of this sign here, right? This l. So we have 2x minus right, and then we have minus left, right? We're left with that. Okay, right minus left is less than or equals to 1. So we just now need to extract x. So maybe do I have still space, right? I have, perfect. All right. So we're going to be left minus 1, right? 2x over right minus left, and then we have minus right, and because of this because of this minus, our left side becomes a plus, and over right minus left side, and that's this. So it's this is 1 actually, and it's already solved, right? You already know this part, this scaling part of the matrix. We had it previously, right? When I was drawing this, right? And then we determined, okay, we need 2 over right minus left, and this is called the scaling part. And now you have also this translation part. So our matrix is going to look like, and now I'm just going to type it for x, but the same applies for actually y. So let's forget about this. So we have our matrix, which is going to be 2 right minus l, right? And here we usually had x, y, z, but we're just focused on an x. So 0, 0, we don't care about it. And here usually we had this term 1. So 1 is actually, when we do the math, is actually here. So we have right plus l, and then right side minus l. So what are we going to be left here? So we're going to have, right, if we rewrite this as a matrix, 2x, right, minus left side, and then y is 0, z is 0, right, gets multiplied here, and here we have 1. So it's going to be minus right plus left side, right minus left side. So we're here. And that's how we can map it, and you're going to see that it checks out. If we just would to type it in our code. So we kind of solved for it, and it already here, the Copilot already gave me suggestions for that, and so we can just retype that. And for y it's kind of same, right? And for z it's a bit different, and you can solve for it. It's a bit different because, right, here space is minus 1 to 1, right? To I'm not sure how to type it. Here it's minus 1 to 1, but here it's 0 to 1 space. So that's a bit different, and you can try to solve for it for yourself if you want to. But let's just type here these values, and I think that solves everything. So that's our orthographic projection. So let's say that I want to move to some space. It doesn't work again, but let's say that I just want to have 0 to be here, and then I want to have maybe here 10. Let's try to do that. So if we go to our, let's just move this to 0, and since our our translation is 0, 0, 0, so our quad should be moved somewhere over here because we're now at the 0, and I'm actually going to do 10 space, and then this was bottom, right? So we want the bottom to be also at 10, maybe, and here 0, and we can just leave this space. And actually it's over here, right? Because I moved it. So now we have 0, 0 space. If I was to move to -1 to 5 space, it would be in the middle, right? So you kind of have this projection now, where you can map to any coordinates that you want. Let's say you want to have the coordinates that go from 0 to 800. You can do that, right? You're just not going to see anything because this thing is going to become way too small, right? So if we are into some weird space, it should still work, but it should be stretched. And let's just move this to -5 to 5 space so that you can see. And then yeah, that's kind of it, right? You can already see how it works, which is perfect. So I'm just going to leave it maybe -10 to 10 space. It's or -5 to 5 space. It's not important. So that's kind of orthographic projection, but we looked more on it not from the side of projection, but we looked on it from the side of mapping, right? We now know how to map from one space to another. So that's how it works. And last thing, I had something in my mind and I cannot remember what actually. Yeah, I remember. I just wanted to showcase this is the space as well, because it might be confusing for some. But I mentioned that our z goes usually from -1 to 1. So if I was to make z at 0. If I was to place z at 1, here it should work. But if it's at 1.01, right, it doesn't work. You're not going to see anything because it's not in 0 to 1 space. And here, if I place it at 0, it works. 0.5, it still works. And if I place it at -0.01, it's below 0 and doesn't work. So that's also about z in these coordinates. So that's it, right? You get the idea. The whole point of this orthographic projection, at least for now, you can think of it as a mapping matrix. And that's it for this video. If you enjoyed it, please like, subscribe, and until next time.